Hello everybody and welcome back. Today we'll be looking at how to use calculus to solve momentum problems. So in this case we'll be looking at the same problem as last time, except what we're going to do is say that this ball is losing mass as it travels towards the block. And so what we're going to say is that the mass, the equation of the mass, is equal to e to the negative 0.1 times time, where t is the time elapsed since the ball has started moving towards the block. And so what this means, if we look at this graphically, is that we have a value that starts at 1, so that's 1 kilogram, and it basically looks like this, where it's approaching 0 as time goes on. But what happens is that it starts at 1. And so this basically represents that the ball starts with a mass of 1 kilogram, and over time it's using, let's call it fuel, to propel itself towards the block to collide. But what we're also going to do is probably put a limit on how much mass this ball can lose, because we don't want it to be entirely fuel, and also that's probably not realistic. So what we're going to say is that when it reaches, this is a very poorly drawn to scale diagram, but when it reaches 0.5 kilograms, it's going to stop releasing fuel propellant to propel it forward. So it can only get down to 0.5 kilograms. And so we can do a few things with this. So first and foremost, we can look at, okay, well, what is the change of mass with respect to time, particularly in this beginning situation? So what we can say is that dm dt, which is the derivative of the mass with respect to time, and then we can use the power rule. And, well, or really, I guess it's the chain rule in this case with exponents. But whenever you have e to the value of something times the variable that you're differentiating with respect to, what you can just do is you say it's the derivative of this top part, which would be negative 0.1, but a constant times the variable, that's always the constant. And then we can multiply it by e to the same thing. So this gives us the change with respect to time of the mass of the system. So what this looks like is it's going to be a slightly less curve right there. And what this represents is that, okay, so at this value, it's saying that there is a negative change in mass. And so if we look up here at the actual graph of the mass, that makes sense, because if we draw a tangent line right here, we can see that obviously the slope is negative, so it is losing mass. And then also what we can say is that the momentum of this system is staying constant, because yes, it's using its own fuel to propel itself. However, that's within the system. So there are no net external forces on the system. So what that means is that the momentum has to be constant. And still that equals mv. But we know that in this case, the mass has this formula. So e to the negative 0.1 t. And then again, times the velocity. So if we wanted to isolate for this velocity, we could, because we actually do know this momentum. We solved it in the last one. If the ball is starting off with 1 kilogram times 10 meters per second, well then that just equals times 10 meters per second is just going to be 10 kilograms times meters per second. And so that's our momentum with respect to time. Just, it's constant the entire time. So if we plug this back in, if the momentum has to be equal to this, then we can solve for velocity. We can say the velocity equals 10 kilograms times meters per second over e to the negative 0.1 t. And again, that equals the momentum over the mass. And so this is the equation for the velocity with respect to time. So as you can see, the velocity actually changes as time goes on. As the ball releases more, it's going to travel faster in order to maintain the same momentum. And so, you know, while I can draw graphs like this that probably aren't that good, it probably would be best if we look at actual graphs that show how these change with respect to time. Unfortunately, there's no collision simulator for us to look at where it allows you to decrease the mass over time, but what we can do is graph it. And what we can look at is the mass, the change in mass, the momentum, change in momentum, velocity, acceleration, and even the kinetic energy of the system, particularly of the ball with respect to time. So here we are on Desmos, and we can take a look at how this collision, where the ball is losing mass over time, would happen. So what we have here is this first graph is showing the mass of the ball with respect to time. And so we have, again, this e to the negative 0.1 times x. We've replaced t with x in this case just so we can graph it more easily. And as you can see right here, we fixed it so that x is greater than 0 just because we're saying that time starts at 0. It can't go before. If it were to go before, it would, you can just get rid of this term. It would look like this, it would just keep going. It's just a regular e to the x looking thing. But we can fix it that x is greater than 0 just so that it's easier to work with. So x greater than 0, as you can see, the mass decreases over time. Now, at a certain point, it will reach 0.5, and we're just going to say that it stops over there once the mass reaches 0.5. And then we can also look at what the graph of the derivative. So this is saying that the change in mass, if we go right here, at the very beginning, is negative 0.1, which makes sense because if we plug in t equals 0, that'd be e to the 0, which is 1, times negative 0.1, which is negative 0.1. So at time equals 0, it is losing negative 0.1 of its kilogram in this first second. And if we look, that actually makes sense because when we get to here, it's roughly 0.9, which is minus 0.1 of its original mass. And so, of course, over time, both of these approach 0. If we were to go on towards infinity, both of these would approach 0 because they're losing mass. But eventually, we're going to cut it off and say, again, at 0.5 kilograms, it's going to stop. Now, the next thing that we can take a look at is the velocity with respect to time. Because remember, what we could find by rearranging the momentum, because it's constant throughout this, is its velocity would look like this over time. So we have 10, which is its original momentum. It's constant over the equation for the mass of the ball over time. And the reason why we're fixing it to be less than 6.931 is because if we go back to this, and if we scroll down here, again, this is the equation for the mass. If we were to set y equal to 1/2, which is where the mass would be half, and we look here, that occurs at time equals 6.931 seconds. So if we fix it to be less than that, what we're saying is that we're trying to find the velocity before it sort of evens out, before it's at a constant velocity. So as you can see here, it starts at a velocity of 10, but as it loses mass, it's going to increase because it's being used as a fuel. The mass is being used as fuel to propel it until it reaches up to 20 meters per second, but at that point, it's just going to stay constant. So the line would just continue along at 20 meters per second because you're not adding any more. You're just maintaining a constant momentum until the ball, of course, collides with the object. But that would be a different mass. It would then have 20 meters per second at a mass of 0.5. And so we could go back to the simulator and try to look at that, but I don't think it goes over 20 meters per second. But of course, you would see different values. But then also what we can do with this graph is find the rate of change with respect to time of the velocity. So this tells us how are we accelerating if our mass looks like this. So what we can do is just take the derivative of this equation right here. And what that looks like is down here. So this is saying that it's accelerating at 1 meters per second squared at the very beginning, and then it moves up until it gets to 2. And it looks like a pretty straight line, but I don't think it's actually that straight. It's slightly curved, but again, it will reach pretty much up to 2 once it gets to that halfway point in the mass where it stops. And the last thing we can sort of look at is the kinetic energy with respect to time. So I believe that's all the way up here. And so this is kind of interesting because it starts off a little bit higher. But what this is saying is that, so over here in this equation, it's 1/2 times the equation for the mass times the equation for the velocity squared. But of course, the velocity is related to the mass. So really, those two are very interconnected. And what that results in is this curve right here, where it starts from 50. So you have 1/2 times the initial, which is 1 times meters per second squared. So that's 10 meters per second squared. So that's 1/2 times 1 times 100, which is 50. And then as the mass decreases over time, the velocity will increase and the kinetic energy will increase, because even though this term is decreasing, this one is increasing and it's squared. So it matters a lot more to the kinetic energy how fast you're moving versus how much or how great your mass is. And so over time, it'll go up, and once it reaches the halfway point, its kinetic energy will be 100, and it will maintain that until it collides with the box. And so we can turn these all on just to get one last little glimpse. They're kind of all over the place, but they're pretty interesting to see. So again, we have this red line here is the mass, the derivative of the mass. Here we have the acceleration. Here we have the velocity. And if we go all the way up, this is the graph for the kinetic energy.